So here we go with example 13. This is the last one in this chapter on application of forces, but again we're looking at an inclined plane kind of context, just like the last one. So, usual routine. Let's go through and identify the key bits in the question. Light inextensible string. I hope you know now what that means, that the tension is going to be constant throughout its length. It's attached to a block A of mass 2 kilograms. The block A is held at rest on a smooth fixed plane which is inclined at an angle of 30 degrees. The string lies along the line of greatest slope of the plane. The smooth light pulley. Again, that's making sure that the tension in the string is constant throughout, which is fixed at the top of the plane. The other end of the string is attached to a block B of mass 5 kilograms, released from rest. By modelling the particles and ignoring it, show that the acceleration is, find the tension in the string, state how you have used the fact that tension is extensible in your calculations, which we've already answered 2 or 3 times in the conversation. Calculate the magnitude of the force exerted on the pulley by the string. So that's the extra little bit at the end. Okay, so as usual, we need first of all to put the forces onto the diagram. So we have got 5G acting downwards, the tension in the string, and those are the same because the string is light and extensible and the pulley is smooth. Got to decide which way we think this is going to move. If we get it wrong, it doesn't matter because it'll just give us a negative value, but the important thing is that we're consistent. But here we're going to take it down there. The 5 kilogram mass is going to pull the 2 kilogram mass up the plane. We've got the weight acting downwards, 2G. And we've got a normal reaction R with the plane. Okay, is there anything else? No, the pulley is smooth. The slope is smooth. So we've got no friction or anything like that. Okay, let's come back to this then. So show that the acceleration of block B is 4/7g. So usual routine then. Apply N2 on B, and we're going to take the down as the positive to be consistent with our acceleration on B. So what are the forces acting on B? Well, we've got 5G acting downwards minus the T which is acting upwards will be equal to MA. We then now to think about block A. So on A, the acceleration is acting up the plane, isn't it? So we're going to apply N2 parallel to the plane and up the plane. And to do that, we need to think about the forces in that direction. So let's go back to our diagram and we can put the components of the forces on. So perpendicular to the plane, we've got, if this is 30 degrees down here, this is 60 because this is a right angle. So this will be 30 degrees. And this is next to it, so this is going to be 2G. Adjacent to the angle is cos of alpha. Okay, now if we look opposite, we've got 2G opposite the angle, so it's going to be sine of alpha. Okay, so we're now going to work parallel to the plane. So we've got this acting parallel to the plane and this acting parallel to the plane. So we are going to get t up the plane minus 2g sine alpha is equal to its maths 2 times acceleration a. And since I put the 2 in there and it's made me look back at what I've done already, there's a little mistake up here. Really, that should have said 5a, shouldn't it? We want its mass in. Okay, what do we notice? As usual with these connected particles, we can now eliminate the tension by adding. So we get 5g minus 2g sine alpha equals 7a. Well, we quite like that 7 appearing because the 7 is matching with the 7 that we're looking up for up there, aren't we? If we just then tidy this up, sine alpha, what's the angle this time? The angle's 30 degrees, so we've got 5g minus 2g sine of 30, because alpha is 30. So sine of 30 equals a half, equals 7 lots of a. So 5g minus a g is 4g over 7 equals a. Meters per second squared. Happy days. So we've got the acceleration of block B. Correct. Find the tension in the string. Well, that's part B. So that was A part 1. A part 2 should now be straightforward. Find the tension in the string. We can just substitute back in, can't we? So we can take that A, substitute it back into either of these. It doesn't really matter which we choose. Let's take that one, and we get 5g minus t equals 5 lots of A, which is 4g over 7. Tidy it up, 5g minus 20g over 7, that's just moving this across, yeah, so subtracting that from both sides, and then we're going to get that's equal to t. Think of the 5g as 35g over 7 minus 20g over 7 equals the tension. So T equals 35 minus 20 is 15g over 7 newtons. Okay, and if you really want to tap that in a calculator, you'll get 147 over 7, which is 21 exactly. I hope, anyway. You can check. newtons, I think that comes out to be exactly. Okay, go back, read the question. Yes, we've answered that. State how you have used the fact that the string is inextensible in your calculations. Well, that's to make sure that the acceleration of A and B is the same. So part B, inextensible, therefore acceleration of A and B is the same. And then part C, calculate the magnitude of the force exerted on the pulley by the string. So if we come back down here, let's just draw it out again. So there's our pulley, and we've got the string acting on the pulley in those two directions. So that's T and that's T. If we come back up to the diagram, and let's have a look here at the angles. So down this corner here is 30 degrees. So this corner up here must be 60 degrees, because this we can think of as a right angle. Okay, so come back down to our little diagram here. This is 60 degrees. So we can split that in half. So that's 30 degrees. That's 30 degrees. So if we break these into their components, remembering the tensions must be the hypotenuse of the triangles, because they're the actual forces that we've got. So this here is T sine 30, and here is T sine 30. So notice they are equal in magnitude, but opposite in direction. So they're going to cancel each other out. So if we have worked in the direction of that green line, that green highlighted section, resolved in that direction, we would get 0. Okay, so what we're really interested in doing is working in this direction. So what forces have we got acting in that direction? We're going to have, well, it's next to the angle, isn't it? So that is going to be, so that bit, whoops. So that bit there is going to be T. It's next to the angle, so it's cos 30. So force on pulley is equal to T cos 30. What have I missed out? A 2, because we've got both tensions producing that amount of force on the pulley. One for the triangle on the right and one for the triangle on the left. Okay, so we know T is 21, so 2, and as it's exact, I don't mind using it. Exact as in with G being 9.8 anyway, and cos of 30, which we know is root 3 over 2. The 2's cancel to leave us 21 root 3 Newton